everyone, my name's Eliza. I am a grad student in psychology and a former teacher, and I'm here to talk to you about stats. My videos are not always going to be pretty, but they're focused on conceptual understanding, and I hope that they help you in your stats and research methods courses. This video will discuss properties of the mean and go into some deeper examples. If you want to learn how to calculate the mean or an overview, I have a video on that as well. The mean may seem like a relatively simple concept, but it's so fundamental to all of our statistics that it's really important to understand how we get to this value and how changes in the data set, even very small ones, will change the mean. So if you imagine a seesaw like I've drawn here, the mean is always going to be at the balance point or pivot point for a distribution so that the seesaw remains even and level. So let's say we have a distribution of 1, 3, 3, 5, 8, and 10. And if you calculate that here, it will have a mean of 5. Okay, so as you can see, I've added each of the values to the seesaw below. And as I said before, the mean is always going to sit at a place where the seesaw remains even. So let's say we had all of our values stacked up on the right-hand side, a whole bunch of 7s, 8s, 9s, 10s, that sort of thing. The mean would no longer be 5. It would have to shift over to the right in order to keep that seesaw level. And that kind of makes sense with our formula for the mean as well. You also want to pay attention to how much higher a certain value is than the mean, because if it's very, very different than the mean, it will have a larger influence, even if you only add one value. So for example, if you added a block at the 10 here, again, your mean would have to shift to the right in order to keep the seesaw even. But if you added a 6, that would be less of a shift. It would still shift a tiny bit, but it wouldn't have to shift as much. Okay, so let's do a demonstration of how these sort of distances from the mean equal out to create the balance point. The number 1, as you can see, is 4 points below the mean. The number 3s are each 2 points below the mean. And then the 5 is at 0, so neither direction. The 8 is 3 points above the mean, and the 10 is 5 points above the mean. You will find that the amount of distance in either direction of the mean in total, the units of distance, will be equal on each side. So as we can see here, if you add the units of distance, not the values, you've got 4 plus 2 plus 2 equals 8 units of distance below the mean, and then 3 plus 5 equals 8 units of distance above the mean. And again, the 5 sits at 0. Another way to think of this, if you, instead of using absolute values, if you use negative values for those below the mean, the sum of all of them will equal to 0. So that shows why you've got a balancing point. You've got an equal amount of distance, units of distance, on each side of the mean, and it sits at the center in that way. We can use this seesaw conceptualization to understand 3 properties of the mean, and this is particularly important if you're doing problems where, say for the GRE, you're short on time, or if you're missing some information. It's really helpful to understand these properties, and even in an applied practical setting as well. So the first property of the mean is that changing the value of any single score in the distribution will also change the mean. Let's say we have a distribution with 2, 3, 4, 4, 7. If we calculate the mean, we're going to get 4. But if we change the 7 with a 10, our numerator increases, but our denominator stays the same. And so our mean goes up to 4.6. If you want to see this on the sort of seesaw example, our original distribution is sitting there where we have 3 below the mean and 3 above the mean. But if you switch it to a 10 from a 7, we now have 5 above the mean. So our pivot point on the seesaw would then have to move up to the right to 4.6. The second property that's good to know about is that adding or removing a score from the data set will change the mean as well, unless the score added or removed is equal to the value of the mean. So let's take our same data set as last time. 2, 3, 4, 4, and 7, which, as you recall, has a mean of 4. But let's add a 6 now to our data set. So we have 2, 3, 4, 4, 6, 7. We now increase the numerator by 6. It has a sum of 26. And we increase the denominator by 1 because we've added 1 to the data set. And if we calculate that, the mean is now 4.33. So if you look over to the seesaw, you now have to shift it up to the right to 4.33. So the mean does change. But it's important to realize that adding a number to the data set will not always increase the mean because you're increasing the denominator as well. So if the number you add is smaller than what the original mean was, the mean will actually go down. So let's look at an example. Let's say we take that 6 out, we go back to our original data set where the mean is 4, but instead we add a 1 in. And so that means our denominator is still 6. We've added 1 to the data set, but our numerator is now only 21. So it only goes from 20 to 21. So when you calculate that, you'll find that the mean is now 3.5, so it did go down, and on the seesaw, the mean would have to shift to the left, down to 3.5 from 4. One more thing to note about this property of the mean is that if from your data set you add or take away any values that are equal to the original mean, that mean will stay the same. So I'm going to give an example of both of those here. So let's say, for example, from our original data set, we take away one of those 2 4s, and then in another we add 2 more 4s. In the first example on the left, you'll see that we have 16 over 4, and the mean is still 4. Sorry, it got a little cut off there. And on the other, when you sum that, it equals 28 over 7. Remember, those denominators are changing because the number of values in the data set is changing. And you again get 4. And on the seesaw example, if you look, you can imagine in terms of the balance, keeping it balanced, no matter how many 4s you take away or add, it's not changing the balance because you're not changing anything on either side. Okay, so the last property of the mean we're going to discuss is that if a constant value is added, subtracted, multiplied, or divided by for every value in the distribution, individual value, the mean will change in the same way. So whatever operation you put of those 4 on each value in the data set, you can also do that to the mean, and it will change the same way. Okay, let's take our same distribution as we had before, 2, 3, 4, 4, and 7, where our mean is 4, if you recall. So let's say we multiply each of those values by 2. So again, each individual value. So that makes the 2 becomes a 4, the 3 becomes a 6, 4s each become an 8, and the 7 becomes a 14. Then we calculate our mean again. So we add 4 plus 6 plus 8 plus 8 plus 14, and our numerator is now going to be 40. And another way to just do that really easily is if you have your numerator from your original mean, right, it was 20 over 5 equals 4, you can just double your numerator as well. That kind of shows it. So now we have 40, the denominator is the same because it's the same number of values, 40 over 5 equals 8, and we do a check, the original mean was 4, the new mean is 8, 2 times 4 equals 8. You can see that it transformed in the same way. Thinking about this using our seesaw example, if you just shift all of these values up and to the right, because if you multiply them by 2, they'll just all shift kind of up and to the right, your mean also will shift up and to the right, and it'll go up to the 8 there. Thanks for listening, everyone. I know that was a long video, but I hope that it helped you understand the mean a little bit better.